So this is chapter 3, vectors and coordinate systems. A lot of this will be review for some of you. I'm assuming you've learned some of this in a math class. But I'm just going to assume that you've never had it before, so we'll just start from scratch. All right, and this is a really short chapter, so beware. All right, so understand the basic properties of vectors. We've already talked about that, magnitude and direction. To add and subtract vectors graphically, we did that, but also using components, that will be new. To be able to decompose a vector into components, reassemble the components into a magnitude and a direction, to recognize and use basic unit vectors, and to work with tilted coordinate systems. So this is just a lot of math, really, but we'll use all of this the entire semester. So you want to make sure that you're not just good, but great at doing these things. All right, so here's a vector. So vector R, and then we've split it into what's called components. So this is along the x coordinate, along the y coordinate. So again, this is the x coordinate of this vector. This is the y coordinate of that vector. So what is a vector equation for this? So you have x, y, r. What's a vector equation for that? So just add vectors. So x plus y equals r. All right? Now, what is this x component in terms of the r and in terms of the angle? Well, just go back to trig. So cosine theta is adjacent over hypotenuse. So therefore, x equals r cos theta. And again, we say that x is the x component of r. Right? Or you can say it's the projection of r along the x-axis. So I mean, you know, if this thing, let's say this thing were sticking out just a little bit, you know, from this slide, from the screen, and we had a big light here, what we would see is we would just see the projection of this vector along the x-axis, and it would just, you know, it would go from here to here, right? So that's the x component, or the x piece, or whatever you want to call it. Okay, let's do the same thing for y. So sine of theta is opposite over hypotenuse. So therefore, so y equals r sine theta. And again, you know, now let's say we have the light this way. And so we shine the light over this thing that sticks out a little bit from the slide. And you just see this here, right? So y is the projection of r along the y-axis, or the component of r along the y-axis. Okay, so there you go, right? So in other words, we can just say r, well, that's enough. Okay, so what I'm saying then is that for any vector A, we can always split it up into components, one along the x-axis and one along the y-axis. And we're going to see later on that's incredibly useful. We're going to be doing it all the time. So we can just say A equals the x component plus the y component. All right? And again, AX equals A cosine theta, and AY equals A sine theta. And you ought to, you ought to know these just like that. You don't want to have to stand here and say, let's see, sine, cosine, SOHCAHTOA, or whatever you guys learned in trig, you know. You ought to just know them just like that. All right. So this is the time where if we were in a regular classroom, we would work together to do this in groups. So now I'm asking you to do it by yourself. Just do what it says. Please find the x and y components of that vector. And you can use a calculator if you need to. Shouldn't really need to, but if you want, that's okay. Okay, so let's do it. So x is equal to the hypotenuse, which is 3 times cosine of 30. So cosine of 30 is radical 3 over 2. And then y is the hypotenuse, 3 times the sine of 30. Times the sine of 30, so it's 3 times a half, which is 3 halves. So we use, we use 30, okay, we use 0, 30, 45, 60, 90, 180, 270. We use those a lot, so hopefully you know what the sine and the cosine and tangent are. I mean, we just use them a lot. So anyway. Okay, so there you go. Okay, now do the same thing. Now, you should all be looking at me like I'm nuts. It's the same answer, right? Because remember what we learned when we learned about vectors the first time. The characteristics of a vector are magnitude and direction. Who cares where it's located? That's completely irrelevant, right? Magnitude and direction. So it's the same answer as this. Just want to reiterate that, all right? Okay, now we want to learn some vector algebra. And this is great. It just makes life easy for us. So it's great. Most of this in this chapter is just going to make life easy, so it's just really, really good. All right, so here's our vector A, x component AX, y component AY. Here's our vector B, x component BX, y component BY. So what we want to do is we want to add the two vectors. We want to add A to B. So we'll do it head to tail. So here's A. So there's the head of A and the tail of B, right? There's B. So head to tail. So that plus that gives you this. We'll call that C, right? Why not, right? All right. So we know that A plus B equals C. Okay, great. So the question is, what is CX? Right, what is CX? Well, you just look at it. So here's C, right? So here's CX right here. But what is that made up of? Well, it's made up of AX plus BX. Yeah. All right, so what I'm saying is, I mean, you can see that on the picture. So what I'm saying is that AX plus BX equals CX. And hopefully, I mean, that makes totally good sense, right? Since A plus B is C, then AX plus BX should be CX. But again, just look at it. AX plus BX equals CX. Right? What's the same thing for Y, right? So here's AY, here's BY, and this whole thing is CY. So we have AY plus BY equals CY, which again should make really good sense. I hope it does anyway. Okay, so here, all right, so as it shows, AX plus BX is CX, and AY plus BY is CY. Yay! Okay, so that's important. I mean, it's really important, Now, what is C? What is C in terms of CX and CY? So that's just Pythagorean theorem, right? So you learned, hopefully a long time ago, CX squared plus CY squared equals C squared. Well, that means that C, we're talking about magnitudes now, right? There's no vector signs, magnitudes. So C is the square root of CX squared plus CY squared, right? Pythagorean theorem. Yes. All right. Now, here's an angle. So this angle is between the x-axis, let's say, and the angle C. So how do you get that angle? Well, the tangent of theta is opposite over adjacent. So the tangent of theta is opposite, which is CY, over adjacent, which is CX. But we don't want tangent theta, we want theta. So you just take the inverse tangent of each side. So theta equals tan inverse of cy over cx. And you better know how to do that, all right, because we use that all the time. Okay, now we're going to learn something called a unit vector. There's 3 of them. And all of this is notation, right? And it's just wonderful because it makes life easy for us, all right? But it's just notation, so it's nothing to get all super excited about, but it is nice. They are nice. Okay, so here we go back to our good old friend, right? Okay, so again, we know that ax plus ay equals a, right? This good old vector addition that we learned some time ago. Now, this is a vector equation, correct? Because we have vector, 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 you know, vector equation. It's not a scalar equation. A scalar equation is like 1 plus 2 equals 3. You know, there's no direction. But there's direction there, right? So it's a vector equation. All right, so what we want to do is learn a really nice way of writing these vector equations, okay? All right, so here is what's called a 3, 4, 5 triangle. You learned about this in trig, right? So this is 4, this is 3, this is 5, right? Because 4 squared is 16, 3 squared is 9, 9 plus 16 is 25, square root of 25 is 5. So 3, 4, 5 triangle. Those are nice, you know, because people like using them in physics problems. And you don't have to do a lot, you know, you don't have to use your calculator. You just know it's a 3, 4, 5 triangle. So it's nice, you know. But anyway. All right, so what we want to do is we want to write a vector equation for the hypotenuse, this vector A. Okay, a vector equation. So here we go. So vector A equals 4 plus 3. Now, is this a correct vector equation? Does it make sense? What do you think? Absolutely not. How can it make sense? You have a vector on the left, you have scalars on the right. I don't see any vector signs, so this is totally ridiculous. It doesn't make a bit of sense. Okay, so what we really need to fix this, we need some directions, you know. We need some directions on the right side. Okay, let's put some directions on the right side. All right, how about this? So we have A equals 4, right 1 unit, plus 3, up 1 unit. Is that a correct vector equation? Yeah, it sure is. I mean, it's perfectly fine. Well, I mean, it's correct. It's not fine, but it's correct, you know. We go 4 units, 1, 2, 3, 4 to the right, and 3 units up. Bingo, we got it. So this is perfectly fine. I'm sorry, it's perfectly correct, but it's not fine. Why isn't it fine? It's too much writing, right? Who's going to write all that all the time? Good golly, not me. So we want to get a replacement for right 1 unit and up 1 unit, and also maybe out 1 unit. You know, we want to get a nice, simple way to write that. So what people have done is they define what's called a unit vector, or 3 of them. There's unit vectors. Now, first of all, unit. What's unit mean? 1, right? Just like this, right? Right 1 unit, up 1 unit. So this is this. This is how you do it, okay? So I hat. So this thing is called a hat. Don't ask me why, right? It's like a up, like this. That's a hat, all right? So this is I hat. So, and you know, you would never do it like this. Never, never, never. Because when you put a little hat on it, it means that the magnitude is 1, okay? So I hat is a unit vector that points in the x direction. J hat is a unit vector that points in a y direction. And k hat is the unit vector that points in the z direction. By the way, we always use a right-handed coordinate system. So if you're a lefty, I'm sorry. We're not going to, you're ignored, okay? Always a right-handed coordinate system. What does that mean? So let's just say that this is x, okay? And then y is up, so y is up, right? Fingers up. And then the thumb is in the k. Okay? If we were lefty, you know, we would say x, y, but then k would be that way, right? So we don't want to be confused, so we always use right-handed coordinate system. X, y, z, right? Okay. Okay, so this is awesome because now, you know, we're just going to say A equals 4I plus 3j, right? I, 1, 2, 3, 4, this way, j, 1, 2, 3, up. Now, what would you rather write? Right? I mean, 4, right 1 unit, plus 3, up 1 unit, or this, right? A, 4I plus 3j. Come on. It's great. It's absolutely great. So, I mean, here's just a silly example how awesome it is. So let's say I have a vector, I don't know, p, all right? Vector p equals 3I minus 4j plus 6k. I have another one, q, equals minus 2I plus 6j minus 5k. Now, how you can do that graphically? I mean, this and then down and over. I mean, oh man, I'm starting to get a headache already. But here, it's a piece of cake, right? So p plus q, you just add them, right? So you add that. 3I minus 2I is just 1I. And you add that. Minus 4j plus 6j is 2j. And you add that. 6k minus 5, or plus minus 5k is plus k. Bingo. I mean, can you be, it's fabulous, right? And if you were subtract, you just subtract. So this is the way to go. I mean, it's simple, fast, wonderful. So pretty much from now on, whenever we write vectors, we'll use this I, J, K notation. Okay, I already said this, right? Right-handed coordinate system, right? Okay, so don't forget that. And it's just, it's only important when we have a three-dimensional problem, which we do sometimes, So just right-handed coordinate system. Okay, I'm sure everybody is familiar with the Pythagorean theorem. I just went over it, right? For 2 dimensions, x squared plus y squared is r squared. But some people have never seen a 3-dimensional Pythagorean theorem. Well, it's not a big deal. I mean, you can look at this slide if you want, but it's just x squared plus y squared plus z squared equals r squared, right? That's all there is, So stare at this slide and you'll see how it makes good sense. But, I mean, you should have had that a long time ago. But if you haven't, now you know, okay? 3-dimensional Pythagorean theorem. And we'll use it once in a while. Okay, I don't want to see that again. Go away. All right. Okay. Yeah. Go away. All right, here we go. Now, pretty soon, we'll be doing something called equilibrium problems. And that has to do with forces and other things, torques. And for forces, equilibrium, it just means that the sum of all the forces equals 0, all right? That's what it means, equilibrium. Sum of the forces equals 0, okay? So, here, and I mean, don't worry about what all this means, just look at the math. That's all we're concerned with now is the math. So here's this force T. It's tension, but don't worry about it. Then this is a normal force, and this is a frictional force, and this is the weight, okay? So we're going to just say that this object here is in equilibrium. So what we're always going to do to make life easy, we're just going to look at the forces along the x-axis and the forces along the y-axis. Just nice that way. All right, and so, we're just going to use a good old, regular plus, minus coordinate system until I tell you otherwise, all right? I mean, later on we'll change. So what we would do for something like that, we would say that the sum of the x forces, all right, okay, let's see, T is along the plus, and the F is along the minus. So we would just say T minus F, and that has to equal 0. Along the Y, this is positive, this is negative. So along the Y, we would just say the sum of the forces along the Y equals N, which is positive, minus W, which is negative. And that equals 0. And then, then we would say T equals F and N equals W and da-da-da-da-da-da, all right? We don't care about that now. We will soon enough, but not now. Okay, so that makes, this is wonderful, right? Everything's along the x-axis. We don't have to do any trigonometry. We don't have to resolve components. We don't have to do anything. Just do it. But you know what? we're not going to have this very often because most things in life, are at some angle. Not always, but sometimes. So here, this is like a more realistic problem, right? So, like let's say, let's say we're pulling something up a ramp or something like that, right? So here's the ramp. This is the tension. We're pulling it up. Here's the weight. Here's the normal. Normal is perpendicular. You should know that, right? Normal means perpendicular. There's the friction. Okay, so, there you go. All right. Now, if we use this, regular old coordinate system, and we want to write, the sum of the x forces equals 0 and the sum of the y forces equals 0, man, it's going to take a lot of work because, we're going to have to decompose this into a tx and a ty. We're going to have to decompose this into a ny and an nx. We have to decompose this into a fx and a fy. Oh my goodness, there's 3 vectors we're going to have to decompose into components to do this, to do this. All right, 3 components you got to decompose. Well, forget it. Why would we want to do that? I mean, there's a simpler way, all right? Instead of using this coordinate system, why don't we just take this whole, let's take this coordinate system, right, and just tilt it, right, or shift it, And so let's use this one. In other words, we'll make this the x-axis, and we'll make that the y-axis. So we're just taking the coordinate system and kind of go, right? So we don't want to use this one. We just want to take this and kind of go shift it. So we're going to use that one. Now, why is that so great? Because now, how many vectors do we have to resolve to get the x components and the y components? Well, this is already along the x, so that's cool. This is already along the y, that's cool. This is all along the x, cool. So look at, this is the only one we have to resolve. So what would you rather do? Resolve 3 or resolve 1? I mean, it's pretty obvious, right? Okay, so that's what we do, all right? We just tilt the axes just to make life easy for ourselves. All right, that's what we do. Okay, now, before we write down the vector equation, we've got to prove something very, very important. So I'm going to copy that on the board. I'm going to try anyway. Okay, so there's the new coordinate axes, and then I have okay. And all I care about right now, I just care about this and this. Okay, well, you'll see. Actually, I just care about this. All right, so again, just pretend that this is some inclined plane, and here's the ground or something like that, right? And so here's our angle theta. Now, when we resolve this vector, we need to know what this angle is, correct? So what is it? So I'm going to show you what that is right now. Okay? So what we care about is this vector, the W vector, Okay? Yeah, all right. So let's do it. So, okay, first of all, let's consider this triangle. All right? So this one. All right? So I'm talking about this. Okay? So let's see. That's theta. This is a 90-degree angle. So what's this? Well, what's the sum of the angles in a right triangle? 180. But we already have this being 90. So this is just 90 minus theta. Right? So this here is 90 minus theta. Agree? All right, because if you add them, you get theta plus 90 plus that one plus 90 minus theta, and that kills what? What? Yeah, which is 180, right? Which is what we want, Okay, so that's nice. Okay, now what I want you to do is consider this. All right? So consider this triangle. All right? Now, obviously, this is the new x-axis, that's the new y-axis, so this is pretty sad. This is a right angle, right? That's a right angle. Okay, so let's let's call this thing phi. Huh? All right? You'll see why, don't worry. Right? So I'm calling this angle here phi. Yeah? Greek, phi. All right? So let's write an equation for this right angle here, you know? Okay, so we know it's a right angle. So it's 90 degrees. So it's made up of this piece, which we just figured out, 90 minus theta, plus this piece, which is phi, right? Plus phi, okay? Wow, look at that. 90 equals 90 minus theta plus phi. So what's true about theta and phi? Well, they're the same, right? So therefore, theta has to equal phi. Okay, so what did I just prove? I just proved that this angle equals this angle. So when we're resolving this vector, we always, we're going to say we're going to get this piece and this piece. This is the angle we're always going to use, but this is the same angle as that. So like in a real problem, they're going to say, they have some slant at 30 degrees or something like that. Then you have to resolve the vector, so this will be the 30 degrees. That's all. All right? So here. Notice that the angle between the w vector, that's the weight, we'll learn that later, and the negative y-axis, right, this, is the same as the angle of the incline. So you just always want to remember that, all right? In other words, this equals that. This is not equal to that, all right? Because, when you're resolving this vector, I mean, you could use this angle, right? Or you get it wrong, you know what I mean? So you always have to use the angle. That's the angle between the new y-axis and the vector. All right? There you go. So this is going to be super crucial. You better remember it. If you don't remember it, you can just prove it to yourself just by doing that little silly thing. Okay, let's do an example. All right, okay. All right, so, okay, what we want to do now is we want to, all I want is magnitudes, all right? So I don't care about the direction, just magnitudes. So this is the y component of this w vector, right? So let's just do it again, So this is the adjacent of this angle. So like we said earlier, what's the trig function that deals with adjacent? It's cosine. So cosine theta equals adjacent, which is wy, over the hypotenuse, which is w. Therefore, wy equals w cos theta. Okay, let's do the other guy, right? So this is along the x-axis, right? And again, I don't care about the direction, just magnitude. We'll do the directions later. So this is opposite of the angle, so that's sine. So sine theta equals opposite, wx all over hypotenuse w. Therefore, wx equals w sine theta. So there you go. All right, so what would we do now? So what we would do, if this were an equilibrium problem, we would say that the sum of the x forces equals 0. Okay, but all right, so what do we have? Along our new coordinate system, we have t is along the positive x. And then this fk is along the negative x. We're going to get a negative. But now there's another one, right? There's this. There's the x component of w. That points in a negative direction. So we say minus wx, which is, but you know, they're not going to give us Wx. You got to figure it out for yourself, right? So we'd say minus W sine theta. There you go. Let's do the y. Again, we're going to say it's equilibrium. Sum of the forces equals 0. So we have n. And then Wy points in the negative y. So we could write down Wy, but we don't know what that is until we do the math, right? So Wy is W cos theta. And there you go. Okay? Now, be really, really careful. When we started out with this component thing, I drew a triangle like this, right? And, you know, we saw that AX is A cos theta, and AY was A sine theta. So I know there are some students that like to think like robots. And what do I mean? So whenever they see an AX, they think has to be a cosine. Whenever there's an AY, has to be a sine. That's wrong, okay? You have to analyze every situation individually. Because look, here, this is a WY, right? It's a WY, but it's a cosine. This is a WX, but it's a sine, okay? So don't think like robots. You know, you got to analyze every situation individually. Okay, let's quit.